second lecture by Carlos Hoyos.
Okay. Let me get the papers. Okay, so we finished before by saying that we need the equation of a state to describe the structure of the star, no? Using the TOV equations, then we can find the profile of the star, and that gives us the mass and the radius, for instance, and other properties, no? That we might want to compute. So all the information about the theory that enters in these quantities is in this equation of a state. And then an important, can you hear it? Yeah, okay. So the important property is the stiffness, which is the derivative of the pressure with respect to the energy density. And usually this is also identified with the speed of sound. Okay, so now this can be seen if you look at the conservation equations for the energy momentum tensor. So if you are in flat space, the conservation of energy in terms of the components of the energy momentum tensor will be like this. Okay, and if you have something like an ideal fluid, then the zero component will be some background energy density plus some perturbation. The momentum will be proportional to a change in the velocity. And the stress will have a background pressure plus some perturbation of the pressure. These two linear order, okay? So if you plug these expressions in the conservation equations, you get something like, no, so the background part is constant, and then you get from the conservation of energy this equation, and from the conservation of momentum this other equation. Okay. So if you take the divergence of the second equation, and then solve for the divergence of the velocity in terms of the derivative of the, with respect to time of the energy. Then these factors will cancel. And then you can use the equation of a state to write this variation of the pressure in this way. Right? And then you just get a wave equation for the perturbation of the energy density. Okay, and then you see this factor corresponds to the velocity of these waves, and these waves are the sound waves. Okay, that corresponds to changes in the energy density or the pressure. Okay. Now, if we want to have a system which is stable, then this quantity should be positive. Okay, the speed of sound should be a positive quantity, or the stiffness. And then causality implies that this speed of sound should be smaller than the speed of light, or equal at most. Yeah. Yeah, this is in flat spacetime. Yeah. Okay, so there are these two conditions on the stiffness. It should be positive, and it should be smaller or equal than 1 in a relativistic theory. So then there is a physical limit on how stiff the matter can be, okay? And this imposes some limits on how compact the star can be, how much mass can it support. No? So the stiffer the equation of a state, the more compact the star can be. Okay, and this is because if we increase the energy density, this means we take some amount of mass and we compress the star, so we're increasing the energy density. Then the pressure has to grow fast in order to compensate for the increase in gravitational attraction. So in order for the star not to collapse, you want that the pressure increase fast, and then you want this equation of a state to be stiff. In a conformal field theory, like we find in the usual formulations of ADS-CFT, we have a word identity for the expectation value of the energy momentum tensor. Okay, if the theory is conformal, then the trace is 0. And then if you plug here the ideal fluid, that gives a condition, which is essentially the equation of state of the conformal theory. So the energy density in 4 dimensions has to be 3 times the pressure. And this means that the stiffness of the conformal field theory, of any conformal field theory, is just 1/3, or the speed of sound squared. So typically, for the stars that the more massive stars one can observe, one needs that the stiffness is larger than this value. So compact neutron stars typically require that this is larger than 1/3. Okay, so in order to have stars like the one we observed, we need that the theory is stiffer than a conformal field theory. Okay, so if we are going to construct a holographic model that tries to describe the matter inside the star, then it cannot be a conformal theory. You have to break conformal invariance in some way. And also, when you break conformal invariance, it better happens that this stiffness becomes larger than the conformal theory. Okay. So now, in this map, one finds that there is a one-to-one correspondence between the equation of a state that you have and the set of solutions of the TOV equations in this plane of mass versus radius. Okay, so there is a one 2-1 correspondence. Between the equation of a state and what is called the mass versus radius curve. Okay, so let's just make a very simple example. Okay, not very physical, but we can do it analytically. So suppose I have a theory where the energy density is constant. Okay, so the energy density is just some fixed value. Now, this means, for instance, that the variation of the energy density with respect to the pressure is 0. So that means that the speed of sound is infinity. Okay, so this doesn't satisfy the causality criterion, but we can keep it as academic example. So this is the stiffest possible equation of a state. No? There cannot be anything more stiff than this. Now, well, to compute the mass is easy, no? Because we can look at the mass function. And now the energy density is a constant. So when we evaluate this mass function on the radius of the star, then we just get the volume of the star times the energy density. So the mass versus radius is just a cubic. It will be something like this. No? And if we are able to observe stars and see that they fall on one of these curves, then we can read from this curve the value of this factor. No? So we are able to observe several stars, the mass and the radius of those stars. Then we can extract the energy density, so we can extract the microscopic equation of a state. Right? We will know by the shape that the energy density is constant, and we will know the value of these constants just by fitting the curve. Right? So in more general cases, we will have some curve where the mass and the radius are parameterized by the central pressure, for instance. So in general, we can have some more complicated curve where each point here corresponds to some parametric so this is a parametric curve in terms of the central pressure. Okay. So in principle, if we are able to measure stars, the radius and the mass of different stars and on different points of this curve, we can compare where these stars are with different equations of a state and see if the equation of a state fits this curve or not. So we can learn which equation of a state we have from these observations. Any questions? Yeah. Okay. So the constraints we have are the following from astrophysical observations. Now we have these constraints from theoretical considerations, no? Just for consistency of the underlying theory, that should be satisfied. Now from observations, so in the first case, we have that the measurements of masses that I mentioned before tell us that there should be stars with masses of the order or above 2 solar masses. Okay, so this comes from pulsars. No, so there are some precise measurements of the masses of pulsars in binary systems, and then the highest masses that have been observed are close to 2 solar masses, a bit above. Okay, so if you have some equation of a state that produces a curve like the one over there, then it is necessary that this curve is reaching 2 solar masses. No? So if, well, maybe I can put it. If we have this case, a curve like this, another one like that. If this is 2 solar masses, then this will be discarded, and this is consistent with the observations, no? Because the equation of a state that produces this curve is not able to give you a star that is massive enough to be consistent. Now, the X-ray measurements from NICER tell us that the radius of these stars are bounded from below to be around 11 or 12 kilometers. Okay, so this is this X-ray. These constraints look more like, you know, there is some likelihood region where the radius of the stars will be. Okay. So if your curve is inside this region, then it's consistent. If it's outside, then it's probably not correct.
Carlos,
yeah.
Remind me, so there's also the Chandrasekhar limit, right? Which says,
it's like,
so if the electron pressure first is 1, so after that you can collapse to a neutron star. I think it's also around 2 solar masses, isn't it?
But for a white star, maybe. If it's the electron, it's a white star.
I mean so the first thing that happens is you win over the electron degeneracy.
Yeah.
Then the next thing is to win over the
neutron.
The proton degeneracy.
Yeah.
And so that's the TOV limit. But I don't remember one of. So I think the Chandrasekhar limit is also around 2 solar masses, right?
I think for neutron is maybe around 3 solar masses, but I don't remember. It's higher than this, I think. But
no,
also,
I mean,
you have to.
So the TOV limit is when you go from neutron star to black hole, right? When you win over the neutron pressure. But before that, you win over the electron pressure to get to neutron stars. So that's the Chandrasekhar limit. But
but this is not describing that. This is just describing neutron stars, not. So just white stars. Sorry, neutron stars. There will be another curve of white stars that will be will have this shape and will become unstable before the 2 solar masses, probably. So here, everything on this curve is a neutron star.
Right. No, but to reach the neutron star, you first have to collapse it past the electron degeneracy pressure, and then get rid of that and retain only the core. I thought that was no?
Well, in the real case, you typically have a supernova, and the core becomes a neutron star directly, I think. if it's massive enough. And if it's
Right.
not massive enough, it becomes a white star. So in this process, there is a bound between when you have a white star and when you have a neutron stars.
Okay.
But this just describes static configurations of neutron stars. So you wouldn't see this Chandrasekhar limit here. No? Yeah.
A type 1 supernova, which is the one that you get once you go past the Chandrasekhar limit, actually explodes. There is no remnant after it. Neutron stars do come out of type 2 supernovae, which are the ones that form after the collapse of a larger star. So I think they don't go through that procedure, that process of. They don't go through the process of go through the Chandrasekhar limit. It's a different mechanism that forms them. So that's the bias.
Okay. Okay, so these are two of the observables, no? The mass and the radius. There is another observable, which is the so-called tidal deformability. That imposes further constraints on the equation of a state. So the idea is the following. You start with some spherical star with some mass and some radius. Okay. And then there is some gravitational wave that comes here on this star, and that deforms the star. Okay. Now, this acquires some quadruple momentum. And then the deformed star can start emitting gravitational waves. So there is an incoming gravitational wave, and there is some emitted gravitational wave. Okay? So the tidal deformability tells you how big is the emitted signal compared to the incoming signal. Okay, so if you expand the time component of the metric in this way, then there is a part which is just the monopole component of related to the mass of the star. There is the polarization tensor of the incoming wave. So this is the incoming polarization tensor. And then there are some corrections. And then there is some contribution from the emission by the deformed star. Okay, so this is the emitted contribution. So this Qij is just the quadruple momentum of the star. No? And the You see the G Newton factor because this is the coupling of the energy momentum tensor to the metric. So one finds that G Newton times this QIJ, this polarization tensor, is proportional to the polarization tensor of the incoming wave with some factor lambda. Lambda is the tidal deformability. Okay. So essentially, it tells you how much quadrupole momentum you produce when there is a gravitational wave coming over this star. There are a couple of definitions related to this tidal deformability that people use that are dimensionless. There is the dimensionless love number. K2. Where you divide by the radius. And then there is a dimensionless tidal deformability. Where it's called lambda bar, which is this love number with some factors that take into account the dependence on the compactness of the star. So this C here is the compactness we mentioned before. It was G Newton mass over radius. Okay, so how do we measure this tidal deformability? So this is coming from binary mergers of neutron stars. So this, if you want, is the definition of the tidal deformability. How to read it from the metric. And what happens is that if we have a binary neutron star merger, we'll have two stars that are rotating around each other. Okay, so at the beginning, there is a phase where they rotate around each other, and they lose angular momentum through the emission of gravitational waves. So they start falling towards each other. So this is called the in spiral phase. Okay, so as they come close to each other, there are tidal forces between the two of them. Yes?
Love number.
Love number. No. No. Yes, maybe you can remember the moment of inertia is also important. So you have the moment of inertia, the quadrupole, and this love number. So people call this I love Q. So these three quantities are relevant. Okay, more questions? Yes.
Thank you. In the case, for instance, when you calculate love numbers for black holes, the obtention of the love number comes from solving an equation that deals on the behavior of the probe field between the event horizon and the infinity, let's say. In the case of these neutron stars, what is the range of around which you solve, let's say, this problem to determine those coefficients?
Well, so the way you do this in practice is like in this kind of procedure, where you assume that the frequency of this gravitational wave is very low. So you approximate this by a static field.
Sure.
Right?
Yeah.
And then you find the solution of the star in this static field, which has this quadruple, and then compute the back reaction of that.
Sure. Okay.
That's how you do it in practice, this calculation.
Okay, and just one more thing. I mean, that love, I mean, usually, I mean, I don't know if in any of those two terms, the love number and the tidal deformability, does that include some sort of dissipation of some sort?
No.
Or no?
No.
No, no, no. Okay. Okay. Thank you.
Yeah. Yeah, that's relevant for the black holes, I think, whether there is dissipation or not. Yeah. Yeah, we'll comment in a second about the black holes. Yeah. Okay. So here in this in-spiral phase, where these two guys become close to each other, they start feeling tidal forces. So their shape is deformed. And, well, the way it is deformed is determined by this tidal deformability. And that affects to the gravitational wave they emit. So it changes the phase and the frequency of the wave that is emitted. Okay, so tidal forces modify the shapes of the stars. And that in turn changes the gravitational wave signal. The emitted gravitational waves. Okay, so in principle, this can be measured in these gravitational wave observatories. Okay. In fact, when they measure this gravitational wave, they are not directly sensitive to this, the tidal deformability of each star, but they're measuring some combination, which is a bit more complicated. Okay, so it's like a combination of the masses of the two stars and their tidal deformabilities, the dimensionless ones. So I'm just putting here the formula, but okay. So, well, then you have some idea of what is the tidal deformability. If you can approximate the two masses as being equal, then what happens is that this lambda tilde, the two lambdas will be equal also, if they have the same equation of state. And then this means that this lambda tilde will be equal to this lambda bar of each star, the dimensionless tidal deformability. Now, it happens that if you have a merger of a black hole and a neutron star, the black hole has 0. Love number or 0 dimensionless tidal deformability, okay, in this dissipationless definition. And then what happens is this lambda tilde will be proportional to the ratio of the neutron star mass to the black hole star mass to the 4 times, assuming M1 is the mass of the black hole. So, and M2 is the mass of the neutron star. So then there is this factor of the ratio of the masses, and typically the black hole is more massive than the neutron star, so this is suppressed. So if you had a black hole and a neutron star merger, then, well, the tidal deformability is very hard to measure, and it has not been, there are no constraints coming from these kind of mergers. So far, there have been only 2 neutron star mergers. Okay, but that gives already some constraints on the tidal deformabilities. Okay, so they are called the number is just the date where they were observed. So they were, this case was observed by LIGO and Virgo. And there was also some electromagnetic signal coming with it. So it was very, it appears in all the news, I think. So this has a lot of publicity. And then this other merger, I think they were not able to pinpoint from which part of the sky it was coming. So they were not able to allocate an electromagnetic signal. So the masses of these objects in this merger were typical neutron star masses of the order of 1.4 solar masses. And then there are these constraints on the tidal deformability. So lambda tilde is around smaller of around 700 or 600. If the stars are rotating not too fast, and if they are rotating faster, then the constraints are a bit different, but of the same order of magnitude. So for a typical neutron star, one expects that this tidal deformability is between 70 and like 580 or something for low spin. Okay, so, and then for high spin is like higher. Okay, so there are these constraints from observations on the tidal deformability. The tidal deformability is essentially determined by the quadrupole momentum, right, of the star that is produced by this external force, and that just depends on the static properties of the star, so it only depends on the equation of state. Okay, so these are more or less the constraints. No? We have some bounds on the radius, we have some bound on the mass, and we have these bounds on the tidal deformability. And then with that, we can constrain the equation of state. Yes.
It's just, it looks like there's one, the first constraint says that the mass has to be bigger than 2 solar masses, and then this observation is 1.4.
Well, this is like, the mass has to be at least, there must be a star with at least these 2 solar masses, no? Like here. You can have stars with smaller masses, but if you...
Like the curve has to reach 2 solar masses at some point.
Yeah.
I see, okay.
That's the constraint.
Cool, thanks.
Yeah. Yeah. What was the question, sir?
The gravitational wave signal is a number, right?
Well, it's a wave. So what you measure is...
But as defined there, is it it's a number, right, or no? The lambda tilde.
Let's say, from the gravitational wave signal, you can read this tidal deformability. Okay.
Ah, okay. Okay.
But the gravitational wave signal is no, so in these observatories, no, you measure. So they are interferometers with that they can measure how one, so they are like a cross. So you can measure how one length of one of the arms of the cross is changing respect to the perpendicular one.
Yep.
So you can measure the amplitude. If that changes if there is some gravitational wave going through it. So you can measure the amplitude, and you can measure the frequency and the phase. So all these parameters depend on this lambda tilde, okay, in some way. But to see precisely how do they depend, you have to solve the Einstein equations, right? And people do this numerically.
Okay. Thank you.
Okay. Yeah. Okay. So these are, so I mentioned these general constraints of the causality and stability. I mentioned these observational constraints. And we have also theoretical constraints that come because we know how at very high energies the theory should be. It should be perturbative QCD. And at low energies, we can apply this lattice or a chiral effective theory. Or we can use observations from nuclear physics experiments. So okay, so here it's convenient to formulate these constraints in terms of the saturation density. So the nuclear saturation density is about 0.15 Fermi to the -3. So this is the number of baryons per unit volume. Okay. And this is defined in this way. When for large atomic number, one can observe that the radius of the nuclei is proportional to 1/3 of the atomic number times some dimension full constant, which is about 1.25 Fermi. Okay, so this means that for this nuclei, if you compute the density, then the baryon density is going to be the number of nucleons, so the atomic number, divided by the volume. And then, because of this relation, then this is independent of the atomic number. So that's the nuclear saturation density. Okay, so this means that the density of nuclei is more or less the same if the nuclei are large enough. Okay, so with respect to this density, there are 3 regimes. First, we have densities which are below the saturation density, and that's where we can apply effective theories, like chiral effective theory. So low densities we have n smaller than the saturation density. we can apply effective theories like chiral perturbation theory. And then for high densities, like above 40 times the saturation density, then we can apply perturbation theory. So then people can compute the equation of a state in these two regimes. They can apply this chiral effective theory up to next to leading order, including nuclear interactions. And here they can apply perturbative QCD also up to next to leading order. So that will mean alpha strong to the cube. Now, in between, we cannot apply any of these things. So that's the part where we don't know what is the equation of a state. And the interior of the heavy neutron stars, this density is expected to be maybe around 5 up to 10. Well, 10 is very large, but around 5 maybe saturation densities. Okay, so it's outside these two regimes. Okay, as we were saying. But maybe 5 to 9. But what should happen with an equation of a state that describes QCD is that at low densities, it should approach whatever you compute using this chiral perturbation theory, and at high densities, it should approach the perturbative result. Okay, so any valid equation of a state should asymptote the low and high equations of a state. Okay, so just to give an idea, let's say you plot here the pressure and the energy density. Then typically one has some band here where this is computed is using the effective theory. Then there is another band at large densities that one finds using perturbative QCD. Okay, and then if you impose the causality and stability constraints, then your equation of a state could be in this region. Okay, so it has to have a slope which is not too small and not too large. It has to be larger than 0, but smaller than 1. And it should interpolate between these two equations of a state. And then when you start imposing further constraints, then you start like cutting into this region. Okay, so observations will exclude part of the equations of a state that are allowed just by interpolation and by causality and stability. Okay. Yeah.
So do we have an expectation that this equation of state should be like a continuous function or not? Because I can imagine that there, at a certain point, a phase transition may happen, so I would expect this curve to be, you know, discontinuous. So yeah. I don't really understand how imposing that so I don't really understand how imposing the two asymptotic behaviors is actually helpful.
Well, so people has taken this into account. What the people that do the general analysis, so if you want agnostic about what the equation of states will be, what they do is the part that you don't know, you parameterize it in some way. So you can, for instance, consider polytropes, so that the pressure is the energy, some constant times the energy to some power. So you divide this region in pieces, like intervals, and you, inside each interval, you approximate the equation of a state by a polytrope, and you play with these exponents and these coefficients, so you satisfy all the relevant constraints. And you allow also phase transitions. So in this diagram, a first-order phase transition will look like horizontal line. Okay. So using all that with many, many possible polytropes, possible equations of states, I'm talking about tens of thousands or more, then they find a band like this. Okay. No. Okay, so when we do a holographic model or try to use holography to describe at least some part of this equation of a state, then it has to be consistent with these observations and these limits, no? In some way. Okay. And if it's not falling inside this band, then it will be excluded. Okay, so how much do we know about this inside the star, let's say? Let me say a few things about the structure. I guess we can plot something like this. So there is this. Okay, so if the radius is about 12 kilometers up to 11.5, so let's say 500 meters, then you have the outer crust, which is nuclei and electrons. Then up to 10 kilometers, you have the inner crust, which is made of nuclei, neutrons, and electrons. And the neutrons are typically superfluid. And then here you have the outer core, up to 3 kilometers or something, where you can have neutrons, protons, electrons, and maybe muons. And then you have superconducting protons. And then you have the inner core, where we don't know what we have. So if you have nuclear matter, maybe you can have neutrons, protons, hyperons, and electrons. If you have quark matter, you could have up-down strains and quarks and electrons. So you could either have quark or nuclear matter. Okay, so what happens here is that as you increase the pressure or the density, then first you just have nuclei and electrons, so that you have some kind of plasma where you have ionized the atoms. Then the nuclei start losing neutrons. Okay, it starts to be favorable to have free neutrons around the nuclei, and then eventually all the neutrons are the matter is so dense that the neutrons are not longer binded inside nuclei. They just move around in some fluid. Okay, so part of this, like the crust and the outer core can be understood from nuclear matter experiments, at least part of it, and the chiral effective theory. And then it's the inner core, especially it's the inner core where we don't know what is the state of matter there, or how it behaves. Now, this matter has to satisfy some conditions. So if you have just nuclear matter, then, so let me put the conditions here. Okay, so if you look at something more than the equation of a state, then you have to impose charge neutrality of the star, which means that if you have a nuclear matter, the density of electrons and the density of protons will be the same. If you have quark matter, you just need that the sum of the charges contributed by the quarks or by the electrons is the same, is 0, sorry. And then the other condition is beta equilibrium. Okay, so we have this process where for nuclear matter, a neutron can decay into a proton, an electron, an antineutrino, or a proton can capture an electron. Okay. So if you want to, this process will change the number of neutrons or protons or electrons that we have inside the star, and unless we have some chemical equilibrium. So that means that this process happens at the same rate as this one. So whenever we produce a proton and an electron, then at the same time, a proton is capturing an electron and producing a neutron. Okay, so this happens if we have that the chemical potentials on both sides are the same. So the chemical potential for the neutrons will be equal to the chemical potential for the proton plus the chemical potential for the electron, in this case. And then for quark matter, the equivalent of this is a process like, several processes like this. Where we can change the flavor of the quarks through this beta process, and then this requires these conditions on the chemical potentials. Okay. So this means that if we have some theory where we can obtain the equation of a state and these quantities, the densities of quarks or the densities of neutrons and protons, then we have to impose these conditions of charge neutrality and beta equilibrium. Okay, as well. So in the end, what these conditions are doing is that, in principle, for instance, if you think about quark matter, and you're at 0 temperature, so this is a good approximation for a neutron star, then you will have like 4 chemical potentials. Your pressure and your energy density can depend on 4 chemical potentials: the up-down, strengths, and electron chemical potentials. However, when you impose these conditions, you end up with a single chemical potential as independent variable. So then the equation of a state depends only on just one variable. Okay, so you have the condition from charge neutrality is 1, and then here, in this case, you have 2 more conditions. So 3 conditions for the 4 chemical potentials. Okay. Good. So maybe I can just mention this thing. Okay, so just to see an application of this, we can see what is the hadronic composition of the neutron star. Okay, just by taking neutrons, protons, and electrons as free fermions. So so if they are free fermions, then we will describe their state by some. If we have a finite density of each of these guys, they will have a Fermi sphere in momentum space. So this will be in momentum space. There will be a Fermi sphere. And of some radius, which is the Fermi momentum. So the Fermi energy, which is the energy of the fermions on this surface, equals to the chemical potential. So mu is just raised of square root of kf squared plus m squared. M is the mass of the fermion. The density, we just have to count how many fermions are inside this Fermi sphere. So we'll have 2 spins for each fermion, and then we integrate over the volume of momentum, and then we have that only momentum below the Fermi momentum is filled. So this is 2 times 4 pi over 2 pi cubed. This integral, so that gives in total kf cubed over 3 pi squared. Yeah.
So first of all, are we taking at 0 temperature limit? because you're saying that the Fermi energy is the chemical potential.
Yes, zero temperature.
And second thing, I mean, the chemical potential depends on the mass of the species considered.
Yeah.
So they would be different than the three chemical potentials. Is it fine?
They won't be different because the Fermi spheres will be different.
Ah, okay. Okay, cool.
So we'll see it. Okay, so if we impose the charge neutrality, the densities of electrons are the same as the density of protons, then the Fermi momentum of the protons should be equal to the Fermi momentum of the electrons, no? Because the density is just proportional to the Fermi momentum to the cube. And then beta equilibrium imposes the condition that these chemical potentials, the neutron chemical potential, should be the sum of the proton and the electron. So this means we have to equate the Fermi energies. Okay, so here we have, in principle, different values of the Fermi momentum, but because of this condition, these two are actually going to be the same. Now, the mass of the proton is around 938.28 MeV. The mass of the neutron is around 939.57 MeV. And the mass of the electron is around 0.511 MeV. So the difference between the mass of the neutron and the mass of the proton is about 1.29 MeV, which is larger than the mass of the electron. Okay, so because of this, if we had that KFP equals KFA equal to 0, so no protons, then we will have a condition here, which will be that this quantity, which is the chemical potential for the neutrons, which should be equal to MP plus MA. But this here is larger than the mass of the neutron. And this here is smaller than the mass of the neutron. So this cannot happen. We cannot have just matter made of neutrons. So we must always have some protons and electrons. But the question is how many, right? Okay, so if we have, let's assume for a moment that we don't have neutrons. That's possible. That will mean that this Fermi momentum of the neutron is set to 0. Then we have a condition of this form. Where I am already using charge neutrality to make this Fermi momentum the same. Now, because the difference between these masses is very small compared to the proton mass, right? Then this Fermi momentum cannot be large compared to the proton mass. It must be small compared to the proton mass. So we can approximate this by just the proton mass. And now we can solve for this Fermi momentum, taking this to the left and then squaring it. And then solving for the mass of the electron. And then if you do the calculation, this is about 1.18 MeV. Okay. So now we can find what is the nuclear density in this case, where there are no neutrons. Just compute the baryon density over the saturation density. This will be the density of protons over the saturation density. And this will be this Fermi momentum to the cube divided by 3 pi square and 0. And this is about 4.5 times 10 to the minus 8. Well, to do this calculation, it's useful to use that the saturation density is about 1.24 times 10 to the 6 MeV cube. No, this way, everything is in MeV. Okay, so in the case with no neutrons, you see that the density is much below the saturation density, right? So when you increase the density above this value, then you must have neutrons. So now what happens if we make the density of the order of the saturation density? Well, okay, then what is going to happen is, in order to increase the density, we need to increase this Fermi momentum by a large factor. And that's going to make this much larger than the electron mass. Right? So we're going to be able to neglect the electron mass. So if we have some density of the order of the saturation density, we expect that the Fermi momentum, which will be of the order of the saturation density to the 1/3, which is about 107 MeV, I think, which is about 1/10 the mass of the proton or the neutron. So this is small compared to the masses of the protons and the neutrons, so we can use a non-relativistic approximation for the Fermi energy. And we don't know the Fermi momentum of the neutron, but it should be similar to the one of the proton. at least much larger than the electron mass. And then the electron we can approximate just by the Fermi momentum. Okay, so now we have a condition that this will be equal to the sum of these two things, right? So we have that the Fermi momentum plus the mass of the neutron, so will be the mass of the proton plus KFP. Okay. And then solving for the Fermi momentum of the neutron, this is this difference. This difference is small. And the Fermi momentum over the mass of the proton is small. So we can neglect these terms, and then we find that the Fermi momentum square of the neutron is approximately 2 times the mass of the neutron times the Fermi momentum of the proton. Okay, so this will be around the saturation density. And then if you plug this in the densities, then you can find that that the total baryon density, which is the sum of the proton plus the neutron densities, this will be given by the Fermi momenta. So this, using these approximations, sorry, this is cube, will be like this contribution from the KFN squared Okay, so here, this I obtained from the formula over there for the Fermi momentum of the neutron. This is small. No, in fact, if we compute the number of protons over the total baryon density, this is going to be like KFP squared over 3 pi squared divided by this number. Yeah.
Yeah, I'm a bit lost. Can you just re-explain what we're trying to get here?
Yeah, I'm going to see what is the proton fraction when the baryon density is of the order of the saturation density. So all this we did was to find the Fermi momentum of the neutron, right? That is given in terms of the Fermi momentum of the proton in this form, with this factor of the neutron mass. And we know that this ratio is like 1/20, so it's small. Okay, so using this, then we find that this ratio is going to be of this order. So this is about 3 pi squared the saturation density over 2mn cube, which is about. Okay, so the proton fraction is non-zero, but very small. If you repeat the same exercise with a baryon density, which is 5 times the saturation density, then you find that the proton fraction is about 5.7%. Okay, so this, if you want, is what is telling us that neutron stars are made out of neutrons. No? It's because of these conditions of charge neutrality and beta equilibrium. No? Using this analysis, we see that in the end, these conditions impose that the number of protons over the total number of baryons is a small number if we impose these conditions inside the star. Okay, this was not obvious before, right? Like, why should a neutron star be made only of neutrons? No, why not protons and neutrons and electrons? Okay, so you can obtain it through this derivation. For quark matter, things are more complicated. If you do the approximation of symmetric quark matter, that means all the masses are the same. Okay, so this is, if the chemical potential is very large, this is not such a bad approximation. Then the conditions are just that all the chemical potentials are the same. And the electron chemical potential is 0. And then the densities are all the same of quarks. And the electron density is 0. Okay? So for symmetric quark matter, you only have quarks. There are no electrons. For nuclear matter, you always have some electrons around to compensate the charge of the protons that you need to have for beta equilibrium. Okay. This is a good place to stop, maybe.
Questions?
Maybe a very naive question. Mm-hmm. So in the entire discussion, we basically never mentioned the possibility of having magnetic fields, and to include magnetic fields into, for instance, the equation of state. And I would say that in neutron stars, one expects very strong magnetic fields to be there. So I was asking myself whether we just decided not to consider them to, have a simpler model, or if there are some phenomenological considerations that might make their presence completely redundant. I do not know. For instance, you were mentioning that in the core there are superfluids and superconducting matter. So basically, there should be Meissner effect. So these magnetic fields would be pulled out of that core. So I just wanted to ask if you could make a comment on magnetic fields.
So there are strong magnetic fields, and also you can consider rotating stars. And that also changes, for instance, the shape of the stars. So here we have just considered the simplest scenario with no magnetic fields and no rotation. In principle, you can add these ingredients in a perturbative way, because even though the magnetic field is strong, compared to the densities of matter you have inside the star, it's not so large. For instance, it's much smaller than the ones you have in the heavy ion collisions. Okay, and for the rotation, it's the same. Typically, there can be pulsars that rotate very, very fast, but when you compute some dimensionless quantity that depends on the frequency, you can do a perturbative expansion in the frequencies. So this is something that, for this, for instance, for the mass versus radius curve, this is an effect which is much smaller than the present sensitivity of the observations. Okay, so it's something not large enough to be important for this kind of observations people have now. So, no.
Other questions? Well, I guess you have 20 minutes to think of new questions, and then we'll meet again for questions and answers.